What's up, algebra bros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get studying! Hey, we're going to talk about Exam 2. We're going to do a bit of our rig rundown, talk about what the expectations are for Exam 2. Hey, you know when this is. Hey, Monday, April 12th. So make sure you're all set up, ready to go for Monday, April 12th during our lecture time. But what are we going to be covering? We're covering our material on chapters 3 and 4. I think this one's going to be pretty nice. Because honestly, chapter 4 is not exactly brand new information, but it's taking some old concepts that we've already discussed and going a bit further with them, embellishing on them. But let's list out the different sections. Let's talk about what we talked about in those sections a bit. Let's try to keep it brief though, because I know, hey, you gotta get out of there, you gotta get studying. So let's just do a bit of a recap. So chapter 3, we have 3.1, which was our introduction to determinants. And we'll go back through and do we'll talk a bit more about these. And then 3.2 was next, and this was properties of determinants. And then we had 3.3 was Cramer's rule. Gotta love it, Cramer's rule. And that was actually it for chapter 3, which brought us into chapter 4. We had 4.1 on vector spaces and subspaces. Yeah. We had 4.2, where we talked about null space and column space, familiar friends, familiar subspaces. You better believe it. That brings us to 4.3, where we talk about linearly independent sets and bases. Brings us to 4.4, where we talked about coordinate systems. And we kept going to 4.5, where we talked about dimension of a vector space. And then bringing us to 4.6, talk about rank. And that's it. That's it for chapter 4. So that's chapters 3 and 4. So let's go through and let's talk a bit briefly about what we sort of encountered in all of these sections. Now in 3.1, we started talking about how to find the determinant. We focused a lot on cofactor expansion. We talked about how we can find determinants of 2x2 matrices, how we can use cofactor expansions to find determinants of larger square matrices. We talked about some special cases, things like triangular matrices, etc., etc. A cool trick that we were able to use for finding determinants of 3x3 matrices, but that it only works for 3x3 matrices. So all of that really cool introductory stuff is in 3.1. So if you aren't familiar with the video, if you hadn't had a chance to really sit down and watch it, hey, now's a really good time to check it out. I don't want you to be left behind. There's a lot of really cool stuff there in 3.1. In 3.2, and actually at the end of 3.1, we started this conversation, brought us into 3.2, we talked about properties of determinants, and here we were really talking about how we could try to incorporate row reduction along with computing a determinant. And For me personally, if you watch those videos, you know that I like to stay away from scaling rows or interchanging rows. And it's not that I don't think it's not worthwhile to do that, but we have to be cognizant of the fact that that will change our determinant, right? If I interchange two rows, all of a sudden my sign and my determinant has flipped. If I scale a row, I'm scaling my determinant by that same scalar. So, you know, I want you to keep that in mind. And you could keep track of everything. You can correct and post is fine. If you scale a row, you can remember to scale it back, should undo any effect. If you interchange a couple of rows, you want to keep track of how many times you do that, for example. Personally, though, I just stay away from that. You can go all the way to a triangular form, and that gives you a really nice result out of the determinant, but you sort of weigh the cost, right? So I personally like to stick with just row replacement, because with row replacement as an operation, we're able to show that that does not change the determinant, that our determinant is preserved, and then I don't have to think about anything beyond that. And honestly, if I'm able to get just enough zeros sort of rocking and rolling in there to help out a cofactor expansion, I'm usually happy. I'm usually happy with that. But if you're trying to go a bit further than then hey, first of all, I'm going to say definitely do it. Second of all, I'm going to say be careful. Keep in mind what operations you're doing, and if they are those two operations that will alter your determinant, keep track of it, fix it. Make sure that you're not getting a wrong answer because of that. But that's sort of what I want to say about the properties of determinants. And this was a really good section too to reinforce what we already talked about 3.1. So 3.1, we introduce the idea of cofactor expansions, and we ended with that discussion on, hey, what do our row operations do to the determinant? In 3.2, we picked up with that conversation, but we got so much more practice with more cofactor expansions, right? So we were really able to sort of consolidate what we already talked about in 3.1 and 3.2. And we were able to take a look at some cool examples in that as well. So really nice sections. 3.3, Cramer's rule. So just going back to these previous sections, make sure you're familiar with finding determinants. Make sure you know what you're doing. Do a cofactor expansion, or make sure you know how to compute a determinant. With Cramer's rule, we need those determinants because now we're talking about building a unique solution, solving a system, right? If that system has a unique solution, we can solve using ratios of determinants. And we have that sort of nice closed form, right? It was the determinant of a sub I b divided by a determinant of a gave me the individual piece of my solution x sub I. If this looks foreign, like it doesn't make sense where this nomenclature came from, hey, watch that video, take a look at Cramer's rule. Make sure you're comfortable using Cramer's rule to compute a solution, right? And that's a really nice way to compute using determinants. Now, there was something else going on in this section that I really want to talk about, and that was talking about finding inverses. So we're able to find the inverse using the adjugate matrix, or sometimes referred to as, depending on how old the text is, sometimes referred to as the classical adjoint matrix. And this is important too, so make sure that in 3.3, not only are you comfortable with going through the steps of Cramer's rule, but also that you're familiar with this process of, hey, I can find an inverse using this so-called adjugate matrix. So definitely really cool stuff. I want to make sure that you're comfortable with it, familiar with it. So I'm talking about that now. Let's do the purple. Let's switch over to purple. And then 4.1, so now bring us to chapter 4, we're talking about vector spaces and subspaces. Remember, to show that something is a vector space, we would go through the 10 vector space axioms. And that's a lot of stuff to check. So we actually had a nice shortcut. The shortcut was, if I can show that something is a subspace of a known vector space, then that's going to act as its own vector space. We actually refer to it as a vector subspace, but it is its own vector space then. And what's nice about showing that something is a subspace is there are 3 properties that I have to check for that. So if I could show that something is serving as, let's say, a subspace of Rn, then that's going to serve as its own vector space 2, which is a really nice shortcut for us because, hey, we don't want to try to show that the 10 vector space axioms are going to hold true. We just want to show these 3 properties. And I apologize if I'm misquoting. You should really check back the video. But I believe it was vector space axioms 1, 4, and 6, the way we have them listed. But you can check back on the video and let me know if that's correct or not. It's 3 properties that we're really checking to show that something is a subspace of a known vector space that gets us to where we want to be with it. That's really invaluable. I want to give a very, very special shout out to a previous section, that's 2.8. And in section 2.8, so this is your sort of inside scoop here, in section 2.8, we talked about subspaces already. And in 4.1, there are a lot of really good examples going through, checking subspaces, checking vector spaces. But in 2.8, we have a couple more, right? So check back on those examples. So I'm going to write a little note here, look into it. Because we had some really great examples showing that things either are or are not subspaces in 2.8. So I think that's worth revisiting this lecture as well. So I'm going to send you back to 2.8. Check it out. 2.8. 2.8 is a great one to take a look at. But then, not to discredit 4.1, there was a lot of cool stuff happening here. We started introducing some new ideas. We talked about polynomial spaces as vector spaces, about how polynomial spaces are isomorphic to our traditional vector spaces. So polynomial space Pn is isomorphic to Rn plus 1. Hey, really cool stuff in there. I don't want you to miss out on that. 4.2. Let's talk about it. We've already introduced the subspaces, null space, and column space. You remember a null space is a subspace of Rn. These are our favorite subspaces, by the way. It's a subspace of Rn, n for null space, and column space is a subspace of Rm, m for the m in column. There's an n in column, but ignore or pretend that's not there. It's silent. Column, m for column space. Rm is the subspace. And we just saw a lot more examples, working with this. We saw some nice set theory definitions as well. We got in some extra practice. I think this probably felt comfortable though, because we've already talked about null space and column space. We were able to build on that more. We were able to take a look at some interesting examples too. So building off of that, seeing examples where we were given descriptions of vectors, trying to describe in terms of null space or column space, trying to sort of elaborate on some familiar ideas already. So very cool stuff, very cool stuff. Linearly independent sets and bases in 4.3. Now we were given some examples where we were given sets of vectors. We were asked, is this a basis for R3? Is this a basis for R2? And remember, we're looking for, building a basis, we're looking for a linearly independent set that's going to serve as a spanning set. And we were able to introduce this idea of linearly independent sets and sort of bring it back to the notion of column space and null space as well, looking for these linearly independent sets of vectors, talking about things like spanning sets. And this should have hopefully been a bit comfortable too. We're sort of elaborating on some things that we've been talking about recently in Chapter 4, but also bringing back to conversations we had back in Chapter 1 when we first talked about linearly independent sets back in 1.7. So we'd already talked about this a bit earlier on in the course too, which is nice. Bringing us to 4.4, one of my favorite lectures is on coordinate systems, and there was a lot for us to sort of talk about here, introducing some ideas, thinking about non-standard bases, right? So we'd say, okay, well, I could have a basis as the, talking about the standard basis, right, with vectors E1, E2, E3, so on and so forth, depending on the vector space we're in. And that's something that we're already used to, right? It's almost like we're designed to think about working in things in a standard basis. And whenever we were plotting points back in pre-calculus or graphing functions, back in calculus, things like that, we were already thinking about in terms of a standard basis, right? I move this much in the x direction, I move this much in the y direction, and that's how we sort of move around our rectangular grid. But that's not the only way that we can travel. We can still have a complete basis for a vector space in a non-standard basis. And that non-standard basis just gives us, we saw a nice example at the end of the lecture here at 4.4, but it gives us sort of this interesting, sort of canted movement, which was really cool. So definitely make sure you're comfortable with the nomenclature in this section. So we have a lot of cool key terms that you want to be comfortable with, right? The change of coordinates matrix, talking about finding new vectors given the weights, right? Given the beta coordinate vectors and the basis vectors, or let's say given the basis vectors and then given the vector x we want to arrive at, how we can then solve to try to find the beta coordinate vector. So just make sure you're comfortable with those sort of approaches, and I have a lot of nice sort of examples in there. I talk a lot about it in depth, but how I like to view it sort of as GPS, more or less, right? Getting directions from someone. How can I travel from where I am to this other vector in the space? And then, how I would travel along the specific roads that I'm allowed to, right? That's really the idea. 4.5, feeling alive. Dimension of a vector space. Now, here we introduced some important ideas, more examples working with bases for column space, null space, things like that, talking about building spanning sets, and then talking about the dimension of a vector space. And this is simply, when I build the set, it's the number of, we'll say, non-trivial vectors in the sets. You got a set of vectors, and they're linearly independent vectors in that set. Count up how many vectors you have. That's the dimension of that vector space. And there were a lot of really cool examples that we took a look at in the section. Some really cool word problems and stuff like that. Make sure that you're checking back over the work that we did in 4.5 and 4.6, where we talk about dimension quite a bit. Because this isn't just a discussion in 4.5, we do talk about dimension further in 4.6. And remember too, important to remember that if I have a set just containing the 0 vector, and we'll use R4 for an example, because we usually pick on R3. R4, 0, 0, 0, 0. If this is all I have in my set, even though there's one vector in the set, because it's the 0 vector, remember we defined, so let's call this set H, we defined the dimension to be 0, the number 0. Now, if it was a different vector, then we have a different story. But if it's the 0 vector, we define the dimension of the set containing the 0 vector to be 0. Which brings us to our last section on rank. And here in the section on rank, we introduced the idea of row space, in addition to column space and null space. We talked a lot about our rank nullity theorem, that if I have a matrix A, so if A is an m by n matrix, then we have the rank of matrix A plus the dimension of the null space of A, sometimes referred to as the nullity of A, is equal to n, the number of columns. And we also talked about row space in this lecture. Now, if you've seen this video, there's a couple of things that I want to address about it now. I just want to talk to you about it. First of all, there was my arithmetic mistake. I think one of the cats was, just mean mugging me, just staring at me, and I must have made a mistake. But I believe I say in that video that 2 plus 5 is equal to 5. Hey, that is not going to happen. It's 2 plus 3 should have given me 5. But a lot of you were very nice, who were willing to point that out to me and accepted me for my failure, and I appreciate that so much. But there's something more sort of, dare I say, pivotal to talk about here, and that's with the discussion on row space. And I want to correct that now. I do want to go back and fix the video, and it's not for you, but you are very intelligent. We're having this conversation now. You've maybe gotten an email and a warning from me about some of this stuff already. And I think that you've got this sort of resorted out, and I'm going to talk about it in a bit as well. But I do want to go back and redo it, and I'll tell you why. It's because it's on the internet. And the internet's supposed to be a safe place for learning, and if there's mistakes on videos on the internet on YouTube, I don't think that that's fair to the the internet as a community. So I'd like to go back and fix that up, make it look nice. But let me talk about row space and an issue that you should take personally with something that I said in that video. And it's very important when building a basis. When building a basis for the row space, you need to use, I'm going to say at least, a row echelon form. So let me clarify. When building a basis for row space of matrix A, you need to use at least a row echelon form of A. Now, if it's in row echelon form and you reduce further to a reduced row echelon form or fully reduced row echelon form, then the span of the rows is preserved from that point on. The issue could potentially come in if you are working with a non-reduced version. And let me give you an example. So let's do a very short one. I've been giving this, a few of you have emailed me a bit about this, and I was happy to talk about it. Let me say I was given a 2x2 matrix A, and that matrix looks as follows. This is matrix A. If I want to do some row operations on this to produce a new matrix B, to produce matrix B, all I would want to do is I would actually want to switch these rows, because hey, I know better. A row of all zeros should be on the bottom, so I really just want to do a row interchange. So I put the zeros. So we swap rows 2 and row 1. That's all we need to do. And this is in fact the only operation I need to do. Now this is in actually a fully reduced form. So it's really just one operation I needed for this example. Now we can see building a basis for the row space of A, and if you watched the lecture 4.6, you know that it's the non-zero rows. So it'd be the first row. So this first row gives me my basis. Now if I take that and say, well, okay, let me use the first row of the original matrix. No, this is a big issue. So this was my faux pas, definitely, of the semester. Don't do this. Make sure it's at least row echelon form, because this could be a big problem. And this is a great example why. It's a very short and concise example, but definitely gets the point across. Now let's say that this row wasn't 1, 3. Let's say it was 2, 6. And then I get 2, 6 and I would scale it. The act of scaling doesn't affect the span of the row vector. So if this wasn't fully reduced, let me actually write down what I'm talking about just to make sure that we're all on the same page. Just get a different color. So now we're talking about how the span is preserved from a row echelon form onward. Let's say similar example, basically the same example. Let's say I had 0, 0, and then this was 2, 6. I still would want a row reduce to produce a new matrix B. That row reduction would be the simple row interchange. Now I can use this to build a basis for my row space. But if I want to reduce this further, I can do a 1/2 row 1 to now build that top row of 1, 3. So this would be fine, this first row of my fully reduced matrix, or my row echelon form's first row, because these are still the same span as far as the row vectors are concerned. Right here, this is just the scalar multiple of it. So once it's in a row echelon form, any operations I do beyond that, the span of the spanning set for row space is in fact preserved. However, if it's not in a row echelon form, there could be an issue. So saying here that, well, the first row is my basis for the row space, that's actually not true. That's actually not correct. So I want to be really clear about this. So here, if I was building a basis, we'll say basis for the row space of A in either of these examples, I think a great choice would just be using the set containing the row vector 1, 3. You could also do the set containing the row vector 2, 6 would be fine as well. But you don't want to just be picking the original rows as they sort of lay in a non-reduced version, because that could potentially present an issue. So hopefully that makes sense. I want to give you something a little extra, because if we remember, for column space, we have to go back to the original matrix. We have to find our pivot columns. We have to go find those pivot columns in the original matrix. None of the other subspace information changes, so that none of those had any disclaimer associated. Row space does, though. Null space, you want to go through a complete reduction. You want to build that parametric vector form of your solution, and then you take those numerical vectors to build your set that way. And then there's row space. So remember, when you're building a basis for column space, so let's talk basis for column space, we want to use the pivot columns in the original recipe matrix. However, if we're talking about a basis for row space, we want to use the non-zero rows. I like to call these pivot rows of at least the row echelon form. I have to do some reduction, and be careful. You don't want to be taking these necessarily from the original matrix because of the issue that we just talked about above. Hopefully that makes sense. If you have any questions on this, let me know. Definitely happy to talk about it. And then we remember that for null space, to build that basis, I have to go all the way through building that solution. Right? I have to go all the way through building that solution, and that's the parametric vector form of the solution that's going to give me the info that I need. And that is about it. So just a few sort of finishing remarks to make sure that you're all set up, ready for that exam. Remember, there's no calculators. No calculators. Bring your blank paper. No calculators. Blank paper, yes. Bring your photo ID. Bring your coffee. Or if you drink tea, bring your tea. Or hey, if you're just drinking Fiji water, bring that. Or I don't know, it's whatever you like to drink is fine. You got Gatorade. If you got a Riptide Rush Gatorade, or you got a Rainberry Gatorade, that's fine. Or if you're drinking Sprite or soft drinks, let me know in the comment section below if you prefer Coca-Cola or Pepsi, or if you also enjoy RC Cola, which stands for Royal Crown Cola. So let me know. Let me know what you like. And I would like to wish you the best of luck. Good luck with studying. Yeah. Probably already started. If you haven't gotten started yet, well, this is me telling you, get started studying. I'm here to help you. Remember, we are on the same side. I'm on your side. I want you to succeed. I know you can succeed. I think you got this one. I got a really good feeling about it. You are definitely the best that we have. You can get it. You can definitely get an A. If you're nervous right now, just stop, relax. Let's do that deep breathing. Let's take a deep breath. I don't think anyone let me know if it's supposed to be in through the nose and out through the mouth, or in through the mouth and out through the nose, or it could be in through the nose and out through the nose, or in through the mouth and out through the mouth. I think the general idea is that breathing is good, and if you're stressed or anxious, then maybe you forget to breathe, and then you start hyperventilating, and I don't want that to happen. You just want to make sure you're breathing regularly. So we'll do nose, mouth, and then we'll do mouth, nose, and let me know in the comment section below which one you found to be more therapeutic. And I could probably just Google this information, but I didn't. So let's do it. So let's do in nose, out mouth right now. Do it with me on the count of 3. 1, 2, 3. See, I like that a lot. But let me try. We're going to do the breathing in through the mouth, and then we're going to exhale out the nose. I have a feeling it's not going to probably be as nice, but let's try it. On the count of 3. We got 1. We got 2. We got 3. You know what? I didn't hate that. I thought I was going to dislike that even more. Let me know what your thoughts are. But just make sure you keep breathing, right? Just, take a deep breath. You are amazing. It's just going to get better from here on out. So, hey, I'm happy with your success, proud of you. Keep doing it. And if you need anything, you know where to find me. So, hey, we're in it together. So let me know. Let me know what you're studying on. Let me know what you're working on. Let me know what questions you have. If you don't have questions, you just want to check in and say, hey, this is what I've been studying. It's going well. Let me know. If you're struggling a bit, say, hey, this is what I'm studying. Struggling a bit. Hey, I'm here to help you, right? So, hey, that's it. Go get studying. Enjoy it. These are precious moments. And I will see you next time. Remember, no matter where you are, who you are, and what you're doing, it's always keep learning, keep dreaming, follow your heart. And I'll see you later.